So, welcome back student. As we are discussing several transformation based strategies, in the last class, last lecture we talk about a very important transformation by using sulfur tether and the reductive desulfurization based method to access it natural products. We will try to explore the similar kind of transformation and little bit unusual transformation which you might not aware of that. So, first we will give you the target molecule which was now we are going to access. The target molecule which I am now going to present having a structure something like this is based on a 6-member lactone, is basically, and then this lactone is having a this alkyl appendage called as appendage, and this is the core structure of a 6-member unsaturated lactones. And eventually this compound, we first draw the retro. The retro as it is says that this final target molecule having a acetate functionality in the cyclohexene core, we will be probably trying to put it as a OH, because alcohol can be easily converted to corresponding acetate by a standard functional group interconversion. Okay. Now, next transformation which I will be drawing, it is a very unique transformation. We first draw the retro, and then we explain what is this transformation. This is the main transformation we will be discussing in today's lecture. Now, it might look very strange to you, definitely. From a furyl carbinol, basically a furan derived compound is a furyl carbinol. Now, if you see the appendages, this particular appendage remains similar, which is basically nothing, CH2 having a methyl, having a vinyl. So, you need some transformation which basically convert this furyl carbinol to this 6-member lactone with a hydroxy group, and the appendage remains same. Now, here the reaction which we will be going to discuss, this particular transformation is named as Akma-Toich reaction or Akma-Toich rearrangement. It is definitely unknown reaction to you. Fine, we will discuss it little bit later on. Now, formulate how further you can do the disconnection. This is a very simple disconnection. We will try to put a furfural and then we will be doing the disconnection here. We will putting a simple Grignard kind of species of this Mg beer. It is very straightforward, and this starting material is commercially available. This one you can again made it by corresponding alcohol. Okay. Now, here is another useful transformation we will be using is called Apple reaction. Apple reaction we will be now explaining that what is Apple reaction, what is Akma-Toich reaction. So, this entire transformation is basically based on these two key transformation, key TF. One is Akma-Toich, one is the Apple reaction. Okay. So, next trying to talk about one by one. Now, Apple reaction is a very useful reaction. Apple reaction will give you a access of corresponding halogen compound starting from a parent alcohol in a single step reaction. Normally, if you have to convert alcohol to corresponding bromide, you can definitely do by PBr3 or other reagent, PBr3 or PCl3, but definitely handling PBr3 and PCl3 is very tough. Those are basically toxic chemical, very toxic chemical. So, do you have a mild version? The answer is yes, you can do it by Apple reaction. Now, Apple reaction, what is the reagent condition? They use triphenyl phosphine and a corresponding CX4, X stands for chloro, bromo or iodo. The mechanism is very simple, you react triphenyl phosphine plus a carbon tetrachloride. I have taken a carbon tetrachloride. So, initially this PH3P tries to attack one of this chlorine linked to this thing, this give you a PH3PA P plus Cl minus plus CCl3. Now, this CCl3 is then try to abstract the acidic hydrogen from this alcohol to become chloroform, and in the whole process this CCl3 minus, which is now remain here, this CCl3 minus will have becomes CHCl3 chloroform. So, then you are having this PH3P plus Cl minus in the reaction mixture, and then you are having this RCH2O minus, because this alcohol now donates the hydrogen to CCl3 minus to become CHCl3. So, that was the main thing. Now, this O minus now attack to this phosphorus, this attacks to this phosphorus with the loss of chlorine atom, and what it gives? It basically gives you RCH2O PH3 PPH3 plus, fine. Now, the Cl minus which have been expelled by attacking this alkoxide to this triphenyl phosphine, as I say, the driving force is making a oxygen phosphorus bond. Remember, we talked about in Mitsunobu reaction, the alcohols are very bad leaving group. You are trying to make a oxygen phosphorus bond. Similar kind of mechanism will also operate in the Mitsunobu reaction. You might have encountered in the Wittig reaction also. The triphenyl phosphine oxide is the byproduct. So, now this Cl minus undergoing a standard SN2 reaction to give you a corresponding halide species or CH2Cl plus triphenyl phosphine oxide. So, this is your final product, you get it in the one step by Apple reaction. Now, this Apple reaction is very useful. You can take this kind of compound depending on the source of this halogen, you will basically get corresponding X. X stands for bromo, chloro, iodo. This is a one step reaction, and I will explain the mechanism. So, now coming to our problem which was given to you, you are having a initial static material CH2 OH. Okay. So, what you do? You basically treat with triphenyl phosphine CBr4, you will basically get the corresponding bromide, react with magnesium 0, magnesium metal basically, and you will get corresponding Grignard, react with furfural. Now, this is it. If you are not familiar with this Apple reaction, does not matter, you can simply do a two step displacement by using it tosyl or reacting with sodium bromide, then or otherwise you can use PBr3. So, now what you will get? You will basically get this compound. Okay. So, this is one of the intermediate. Now, next we will try to visualize what is the Achmatoich reaction. So, now we will try to visualize what is Achmatoich reaction, because in this furan carbinol you have to do the Achmatoich reaction. Now, Achmatoich reaction is a very useful reaction. I will draw a furan compound, substituted furan compound. And the furan must be having this kind of structure. The furan must have a alpha hydroxy, it is basically carbinol structure, furan carbinol. Then you take this compound, react with MCPBA, metachloroperbenzoic acid. It was initially postulated that this one of these electron rich double bond in the furan first undergo epoxidation reaction with this parent furan. I take a simple furan like this, and then reaction something like this takes place to open up the epoxide. So, basically now opening up the epoxide, try to put the proper arrow. This oxygen now becomes oxonium species, and you are having this OH and phenyl here, and this epoxide basically opens up to give you this alkoxide, epoxide opening, simple epoxide opening. Now, this epoxide now can open up in this way to open up the furan ring. Now, this part is crucial. You will basically get a methyl here, fine, and then here you basically get a aldehyde from this. This part is oxonium ion, basically a ketone. So, basically a ketone, and then you are having this carbinol structure. So, furan ring must have to open up, okay. And then you see there is the hydroxy, there is the aldehyde, there is a hydroxy, there is a aldehyde. So, this alcohol now undergoing a intramolecular nucleophilic attack, which is similar like a when you form say acetal or ketal, and then basically you will get a 6 member thing, you will basically get a 6 member thing. You try to formulate exactly what is going on. It is a very important transformation in the whole pathway. So, basically you try to attack there. Now, see 1, 2, 3, 4, 5, 6. So, this way basically you are getting a 6 member things, and then it is a normal this oxonium ion species, and this MCPBA, this corresponding carboxylic acid remains here. So, this basically picks up this hydrogen, and once it picks up this hydrogen, the final product which will come will be having a structure this groups remain same. You will having this hydroxy here, and you have a these things, and then you are having this phenyl. So, this is basically your 6 member lactone, 6 member lactone. And now we will come back to the original problem, where the structure of this after this apple and grignard, which is the furan carbinol, is basically these things. We will try to simplify it by putting the entire group as a R. So, we will now write these things as a OH R. Now, subject to this starting material to this Achmatoich reaction, Achmatoich by MCPBA, okay. And then After this Akmatowicz reaction, you will get the compound, the 6-member thing as we explained earlier. This R group is basically this group. This R group is basically this group. So, you are very close. Now, what you need to do? You just need to do a acetylation to put this acetate group here. Now, as I said, if you are not familiar with this Akmatowicz reaction, this will be very difficult for you to think. That is why more and more reaction you know. Now, this compound is basically nothing, our target molecule. You now try to put all the groups in a proper structural viewpoint. You see this group is this group, and then you have this methyl and you have this group. So, this was the target molecule which we initially drawn. So, Akmatowicz reaction is basically the main or key transformation, and in addition you are having a Apple reaction. So, both the transformation we are using it here. So, entire pathway if I now draw it again, the entire pathway, the target molecule was this, and then you are having this is the target molecule. So, the transformation, key transformation which you are using here, first one is the Apple reaction, Apple transformation, and second one is the Akmatowicz. Now, Akmatowicz reaction was basically named by this inventor Akmatowicz, who is a Russian scientist, and eventually you can use this Akmatowicz reaction by treating this furyl carbinol with MCPBA. There are other reagents also which can facilitate this Akmatowicz reaction, and then that will be probably give you a very nice access, this OH basically this kind of compound. This is OH, this is OH. So, Akmatowicz reaction is very useful, and eventually you can access this kind of compounds. And Akmatowicz reaction, if you go to the Scene Archive website, you will find its mechanism, and you can explore that if Akmatowicz reaction was sometimes used for the synthesis of many natural products. So, this is the powerful transformation probably not known to you. Apple reaction is a simple one, but Akmatowicz, this transformation, if you are not familiar with, that will give you the idea that this simple transformation. So, the starting material is pretty simple, the reagent is pretty simple, but the final product, which is definitely you have to think about how this furyl carbinol system reacts under this oxidative condition to give you the rearranged product, which is having this pyranone structure. It is basically 6-member lactone, sometimes called pyranone. Now, this is the beauty of this powerful transformation which helps you to deal with. We will stop today's lecture by discussing another simple problem, and then we will try to analyze how this one was done. This particular compound was used as a target molecule, or was given as a target molecule, and if you see the structural features, is basically a 5-member ring and a 7-member ring fused together. Now, as I said, it will be purely transformation based approach. Let us first do the retro. Now, this reaction might be known to you, might not be known, we will figure it out. You see, the first retro which we draw is based on this kind of transformation. We see the ring A and ring B. Earlier we explained that cyclopentane containing starting materials are easily available. So, we kept out the cyclopentane containing things as a ring A, and then the reaction which we will be discussing here is basically known as carbonyl ene reaction. It means that this hydrogen of this compound will undergo a hydrogen transfer from this to this carbonyl. The ene reaction is basically a pericyclic reaction. I am just trying to figure it out what is ene reaction in a simplified version, not in detail. So, this is a ene reaction. This is basically called a ene, and this compound is called enophile, similar like diene and dienophile. Now, this reaction basically says that you try to close or make a so this hydrogen which was here now have been shifted at this end, similar like this. The hydrogen is here, and eventually for ene reaction is a kind of a pericyclic reaction. Is kind of a pericyclic reaction. Is a pericyclic reaction, and you will find that effective homolupo orbital interaction is needed. You need a homo of the ene and LUMO of the enophile will interact in a very efficient way. So, probably this homo LUMO drawing we can just now simplify it. If you are familiar with this homo LUMO thing, you can draw this homo of this particular ene, and this is the homo of the ene, and then this enophile will trying to draw its LUMO. We have the similar kind of color, the red color, which indicates you have a maximum overlap, and this hydrogen particularly is having here hydrogen. So, that basically makes this perfect overlap, and this is similar electron density, this homo LUMO overlap. So, that is a homo of this ene and LUMO of this enophile will make this ene reaction. So, in principle this is the very important reaction. It is named as carbonyl ene reaction because one part you are having this carbonyl compound. Okay. Carbonyl compound as a enophile. Fine. So, now we will explain the starting material or intermediate which we have just drawn now. We said we will be having a ene kind of reaction if you have this particular substrate. We will draw the structure in this way. Okay. So, this is the now we will simply do it a functional group manipulation or functional group interconversion. How we will do it? We will put remaining groups all similar. We will try to convert this aldehyde by a functional group interconversion which we explained earlier. Treat the cyanide, if you have cyanide, react to it diol, fine, that is a FGI. Next, what we will do? We will check it. If you have this compound, you have this methyl, and if you have this starting material. So, basically we are trying to now figure it out if you can think about a doing a Michael reaction. The Michael reaction with whom? Acrylonitrile. You can generate a stable thermodynamically different enolate here, and this enolate will react in 1,4 fashion to give you this compound. Now, this was, you can simplify it to a starting material, a cyclopentenone based starting material, which is this, and you can think about doing a simple Gilman reaction, to put this compound. So, this is your starting material, is absolutely easy starting material, commercially available. So, now let us draw the forward pathway. So, what you are having? You have this starting material. This starting material is there with you, and you are reacting with this thing, corresponding Gilman reagent. Okay, it is methyl. Do a 1,4 Gilman. You can do a 1,4 Gilman. So, means that these things will attack here, and then you come here, you have these things, and now once these things will basically, you have this O minus, and then you have this Gilman. Okay, this methyl is here, fine. So, now you can put this acrylonitrile as required by you. So, it can go back, it can react in 1,4 fashion, and that will basically give you this part is similar, your CH2, CN, and the final target, this ketone was not like this, it was kept as a protected. So, what you do, you just use a sodium borohydride, which will reduce the ketone, and as step 1, step B, you just protect it with TBS chloride. So, you can do a OTBS, and then you figure it out. This is, so next you are almost close to the carbonyl reaction. What you do? You do a simple Diebol reduction to convert the cyano to corresponding aldehyde. So, we will convert the cyano to corresponding aldehyde, this. Okay. Now, everything is ready, you can now visualize the in reaction, So, what to do? As I said, the in reaction is basically a thermally driven reaction, and so then you basically have a in product. This is called carbonyl in reaction. It is a carbonyl in reaction, and then this double bond will be generated. You have these things, it is CH2, it will basically the OH. Now, see, this is your target molecule, this is the target molecule. So, a complex structure, we are simplifying it by using a series of reaction. So, the key transformation what we use here is basically a carbonyl in reaction. So, carbonyl in reaction is a, as we explained earlier, it is basically a hydrogen shifting from one end of the molecule to another end when you have a enophile. So, this is in, this is enophile, and then this basically undergoes these things to give you the 7-member ring. So, carbon lead reaction was one of the reaction, and then this is the main transformation. In addition, you use other transformation which is nothing but a Gilman reaction of a suitable nucleophile. So, in this case we are using a Gilman something like this copper lithium, and then we are using on the same pot we are using a Michael reaction with acrylonitrile, that basically gives you CH2CN. This CN has been converted to CHO, and then we do simple functional group interconversion to reduce this carbonyl group to alcohol, and then we convert this to a suitable protecting group TBS, because our final target structure having a TBS. So, see this simplified things was, you take the target molecule, we take the target molecule and you devise the retro. This is the target molecule. We have simplified the target through a in reaction, and then we have basically made your life quite simple. So, fine, we will keep on discussing several transformation based strategies through this kind of problem solving approach. I hope all of you are enjoying it, and if you have any difficulties we can definitely come to open forum. Till then, try to solve the assignments. Until then, have a good time. Bye.